This is DNS Security. This is the second class meeting. There are only a total of 6 meetings. Went through the first chapter here, and now we're down to 2. As you see, there are going to be just a few more chapters, and you should start taking the quizzes online and doing the hands-on projects. So I'm going to start with the first chapter here. All right, and if you guys can hold it down over there, that'd be good, so it doesn't get too much noise here. Okay, anyway, so, all right, so DNS Security is here, and so we're going to talk about the history that led to this. Now, in the early days, there was no DNS. The internet was small. It started with only 4 servers, and people just had a floppy disk that would list these servers on the internet, and they would just mail this around, and that contained a hosts file. And machines still have a hosts file in them, but it's typically empty and not used anymore, but you can, in principle, put IP addresses in the host file, and that will be trusted by your machine, and it's one way to block malicious websites. Anyway, so DNS started in 1983 as the internet grew too big for that, and now the idea was the list of the connection between domain names and IP addresses will be online and constantly updated as the internet is growing faster and faster. And so there will be a distributed system where many servers all contribute to it so that it stays up even as individual machines go up and down. So there's the DNS name structure. You can have up to 4 labels separated by dots. So here's a fully qualified domain name. You have a host name followed by a domain followed by a top-level domain, which is edu. So, and you could have another one before it. You could have something else, .hills, .ccsf, .edu. That's the whole structure of a domain name. And so that's the hierarchical space. So you have the root of DNS, which is dot, and all that has is the address of the top-level domain servers, like .net and .com and .us, and each one of them has the IP addresses of the name servers, the authoritative name servers for all the companies under there, like example.com and ccsf.edu and so on. And then those authoritative servers have the machines within that domain. So that's the hierarchy. And those things are called a DNS zone. So if you have a CCSF DNS server, it will have a zone which will be these parts of the CCSF domain, typically the whole thing, and it'll have a zone file that has the IP addresses for that, and that's what it is authoritative over. It's authoritative over its zone. You could, at a bigger company, you could split it into pieces. Like we could have a separate DNS zone for Ocean and Mission and Evans campus, and then we'd have 3 different sets of domain DNS servers, each controlling only part of the company, and that's what your bigger company would do. And so the parent domain would then delegate responsibility for a subdomain down to another one here. That's DNS delegation. All right. So a DNS client is something running on your computer that you're using to find domain names so you can search the web and connect to things. A DNS server stores and serves DNS data, and a DNS resolver is what you have in your router at home. It is just sort of a proxy that takes requests and then forwards them to a server somewhere and gets the answer for you. So authoritative servers have the master copy of information about a domain that's called the start of authority. And so you might have multiple servers, but one of them will be the authoritative one, and the others will just have copies of the data from the authoritative one. Now, so if you have end-user hosts at a company, they'll typically go to a caching DNS server, which means it remembers data temporarily. So if any people go to the same page like Google, it doesn't keep asking where Google is. It knows where Google is. And then it will send iterative queries off to hunt through the internet to find things. And so it will, you send a recursive query here. A recursive query means find out, even if you have to ask a lot of other people. An iterative query, I think, asks just one source. So I'm not quite sure about the difference between iterative and recursive. It may be coming up in a later slide. All right, anyway, the cached records have a time to live, and you can see it. In fact, I should be able to do that live. Let me get a terminal here. Should be kind of fun. If I dig Yahoo, we should be able to see this. Dig yahoo.com. Yeah, notice this number, 889, for these Yahoo addresses. If I just dig it again, now it's 883. It's gone down by a few seconds. So you can watch the records expire. This is how many seconds they have to live. So now it's 874. So what I'm seeing is cached information at some local server, City College server, and when this counts to 0, it will throw away the cache and get a fresh copy. And that's why when you design your DNS, you specify this time. And if you make it a long time, then your server will get less load because people will rarely ask it for, but then if you move something, it'll take a long time for end users to find it because the old cached information will last longer. So anyway, you can just see the time to live right there. All right, so here's the difference. A recursive server means find the answer wherever you get it. It will not respond with a referral to another server. An iterative query will tell you if it's on this server, and if not, it'll send a referral. So the requester has to send another query to find it. That's the difference. All right. So normally, as an end user, you do recursive queries. You ask your router, go find it and tell me the answer, and I don't care how many servers you had to ask to find the answer. All right. And let me just check the Twitch to see if there are questions. Apparently not. All right. Okay. So a forwarder just forwards DNS queries to another machine, and this is just a way to, it can cache more records. It's just a performance issue if you use a DNS forwarder. And the DNS resolvers receive requests from client applications and query servers to find the answer for them. And there is a stub resolver, is a resolver connected to only one recursive server, and this is typically what you have at home. You have your router, you connect it to your ISP, and they give you one DNS tier to use, and you just use that one. Although they probably give you two addresses just in case one of them is down, but that's the point. And you can also, Windows is a stub resolver, and Linux is a stub resolver, where it just, and Windows has a DNS cache. So you can clear it with ipconfig/flush DNS. Linux does not cache DNS at all. Every time you go to a website, it asks for the domain, for the IP address again. All right, so you can make a local DNS server. These are your local DNS server addresses. You see it down here, DNS servers 192.168.119.2. This is just going to a local router. That's typically what you have. If you have DHCP turned on, then it dynamically assigns this every time you connect, and that's the normal situation. You can configure it manually, but that's something you normally only do in a lab like this where you have heavy machines tied to a desk. Machines that are moving, you want it to automatically configure. All right. And all right, so here's typical name resolution. I'm in my operating system has a stub resolver. I want to find www.ccsf.edu. I ask my local DNS server, which is my router, and it then goes through the steps. If it doesn't know where edu is, it will ask the root, although it probably has that cached. And then it will ask edu, where is ccsf.edu? Where's the name server for that, the start of authority? Then it will go down there and say, okay, you're the boss, where is www.ccsf.edu? Although it might not use the start of authority, it might just use a random name server. But that's what it'll do. It might take up to 3 requests to find it, but if it has cached information, it would need less requests. All right, so the master server contains the primary zone files. Then you have slave servers that have copied them, although I think people are trying to change these terms to be less offensive. I'm not quite sure what the new terms are. And this is called a zone transfer, copying the zone data from one DNS server to another. All right, I'm just checking my progress here. All right, I think I'll wait a little while for doing the first Kahoot. All right, so the root server is named .dot. That has pointers to the top level domain like .com and .biz. And you would only ask that if you don't have any data in the cache, typically after you just rebooted the DNS server and it's forgotten everything. All right. Then the root server is actually hundreds of servers with 13 domain names dispersed around the world, which is why it's never gone down. And then we should talk about the DNS resource record types and classes. Each piece of data in DNS is called a resource record. The normal one, the most famous one, is A. An A record is an IP address. That's normally what you want. IP version 6 uses quad A. MX is mail exchanges. PTR is an alphabetic host name corresponding to an address. And NS is a name server. Not necessarily the SOA, but a name server. And CNAME is a canonical name, which is a name that can forward to another server. And you can put up text records with just general information. So those are the most common resource record types in DNS. There are others. Here's some less common ones. Service for application, sender policy framework used to control spam. The SPF records helps your mail servers tell if email has really come from a server that should be sending that email from the from address. And then there's the DNS sec records down here, DNS key, DS, RRSig, and NSEC. These are all cryptographic signature records that help your DNS server verify that it's getting accurate data, if it's using DNS sec, which many of them are not yet. So if you do a dig any of ccsf.edu, you'll see various bits of information. Let me try doing it live. The any is being deprecated, but it might still work around here. Yep, any is still working. Some servers won't let you do any anymore. And so it gives me a lot of information. Text, SPF, mail server, IP version 4 address, start of authority, and another name server. So here's what a text record looks like. And it looks like it has the same thing as the Sender Protection Framework record. And you have to put this on if you want to have Outlook mail going from your servers. And you have to get it just right, or people will refuse to take the Outlook mail. All right. And IETF, that's right, IETF is, City College is not using DNSSEC. It doesn't have any of that cryptographic stuff. If you do IETF.org, then it does give me a resource record signature, which is this long blob of base 64 junk. That's what it looks like, and that's why the answers are a lot bigger. So it will give you information, and it will give you signatures to verify that information. All right. And if you find that your local DNS is filtered, which it often is, you might use a DNS looking glass. One of them is Ring of Saturn. Let me just bring that up so you can see it. Starbucks messes with DNS, and a lot of people do. Ring of Saturn, DNS looking glass. There it is. A lot of people let you do this so you can get unfiltered DNS, even if your environment is heavily filtered and limited. So I can do a dig of any at IETF.org, for example, and let's see what it gets. It might be different than what I got locally, and it is different. See, I got all these extra DNS records. City College only gave me a small portion of this data. So if you want good, clean DNS information about the web, you often use these looking glasses that are outside your firewall, going directly to the internet without having whatever filtering your local network has. All right. And then there's reverse DNS resolution. You can start with an IP address and find the domain name, and this is something people do to try to block spam email. That works by using these records called inadder.arpa with the IP address backwards. So the 147, 144, 1212, which is one of the City College addresses, the reverse lookup uses this entry, the IP address backwards, .inadder.arpa. It's very strange, but that's what the reverse DNS records look like. And you can do that with a dig -X. So let's give that a try. If I do a dig, let me just do a clear first. All right, make this a little bigger. Okay, if I do a dig of www.ccsf.edu, that's giving me a 54, that's annoying. All right, I'll just use Hills. Hills gives me an old-fashioned address. I don't know what that new stuff is. There. Up. I gotta have Hills spelled better. Hills is one of the old servers here. All right, 147, 144, 12. Now I should be able to do a reverse lookup. If I do a dig -X of that address, 147, 144, 12. Yep, and it works. So I did a reverse lookup starting from the IP address, and I got the alphabetical name of that. So if you do configure reverse records, then they will pass this test, and these servers are far more likely to be able to send email and such. You're not required to configure them, but anytime you have a public domain, you typically do want to configure these reverse records to make this possible. All right, there's a forward lookup for Google, and maybe I got a reverse lookup for Google. Yeah, reverse lookup for Google. So here I did the IP version 6. Let's try that. Let's do the IP version 6 version. So I do dig AAAA for google.com. I'll do www.google.com. All right, so there's the IP version 6 address. So I'll copy that, and now I can do a dig -X of that IP address. And it worked. And notice, by the way, IP version 6 is even more of a mess. you have to take this whole blob of hexadecimal and every single character backwards with a dot in between it. So the in-ARPA record is ridiculously long, but it did find an alphabetic name for that domain, although it is not www.google.com. It's this, sfo362 something.net. So things, www.google.com is probably an alias, ultimately pointing to this. But it was able to find a reverse lookup. It's just not obvious that that's Google. All right. And that's also what I found before, it's some kind of SFO address for it. All right. So let's try a Kahoot. I think we got enough to get to the first Kahoot here, which is here, CNET 40, 2A. All right. All right. Oh, yeah, there should be a Trump mug shot by now, huh? I haven't seen it, but I think he's turning himself in right about now. I'll give it a few more seconds. That's why I thought a few more people coming in. All right. Okay, wait a few more seconds yet. All right, so what system did name resolution before DNS? Yeah, the hosts file. All right. So which of these is a top-level domain? Yep, the .info at the end. That's the top-level domain. All right. All right, which of these is a fully qualified domain name? Yeah, the complete one. The name of the host, the name of the domain, and the top-level domain. All right. All right, so what device stores all the DNS records for a zone? Yeah, the DNS server has a zone of which it has data, and it has a zone file for that. That's where the data comes from. All right. All right, so you add a new server. Where should you add its DNS record? Put it in the start of authority, the authoritative server. It will then be copied automatically to the other name servers by zone transfers, and other servers that look for it will cache the records when they want it. But this is the start of everything. This is where you put new data, which will then be copied to other servers in the course of time. All right, so what process copies all the records from one server to another? That's called a zone transfer. And Microsoft, in their wisdom, used the same word for an Active Directory duplication because they're like that. But anyway. Jamie D. Well, we'll have to tell me who they are if they want their points. All right, good. All right, so let's go back to the slides. So here's a layout of this. You have the root of DNS, and let me get rid of this stuff. Then you've got top-level domains, and then you have ARPA and inadder.arpa for the reverse DNS lookup. So that's how it looks. All right, and here's a DNS packet. You have a header with like a transaction ID and the question, then you have repeats the question, then it gives you the answer if there is one, then it gives you authority records saying what server it got this data from, and perhaps additional records like delegation. These are not always present, but these are things you'll find. So the header format, it's got a 2-byte transaction ID, which is a number up to 65,000. And then some flags showing whether the response is authoritative and other things. And then the number of questions, number of answers, number of authority records, and number of additional records. Notice there is no password, there is no encryption, and there is no credentials. That's a problem at DNS. Like most internet protocols, it was just designed to function, and security was tried to patch on later in an ad hoc way. Here's some flags. You have whether it's a query or response, whether it's forward or reverse, and whether it's recursive or iterative. Those are some things that are in these flags. All right, now there are glue records, which are pretty mind-boggling, but think about this. If the start of authority for ccsciv.edu is ns3.ccsciv.edu, it'll never work, because suppose you have at a company and no one's ever been here before, you go, where is ccsf.edu? It says, well, ask ns3.ccsf.edu. Well, where's that? Well, it says ask ns3, right? You'll never find it, because you would need to know where ccsf.edu is in order to find the start of authority. So this means every domain has to have a glue record up at the edu level, in the top level domain, and that has to specify the IP address of the start of authority. So it can send you to the start of authority for that domain without having to ask anybody, and that's quite a lot of data. It's in fact a huge amount of data, and there have been a couple of crisis points when the amount of data required for this exceeded the storage of the available DNS servers, sort of like the Y2K problem. There have been a couple of crises like that. Anyway, that's the way it is. It's kind of a crazy system. So you can view them with dig. First you find an edu.root NS server, and then you can do dig ns at domain.root, and then you can find the IPv4 for Google. So you dig ns for .com, and you get the .com servers, and then you go to @m, looking for the name servers, and I'm not sure I understand how this is working. The name servers, There we are, bind version query. Well, I didn't actually see where we got the glue record there. Maybe some way to make this quieter. All right. I don't understand my own notes here, how we got the glue record. Viewing a glue record, you find a server, then you do dig NS domain at root. And I guess this is the glue record. I see, there it is, NS3. NS3 is, okay, that's how it works. Let's try doing this for ccsf.edu so I can make it clear. So I want to find an edu top-level server. So I dig NS edu. Yep. All right, here's the edu top-level domain servers. Now that I've found them, I can choose one of them, and now I dig domain at root. Okay, so it's dig ns ccsf.edu, ccsf.edu, but I'm going to do it at the top level. That should do it, and it does do it. Okay, now I understand what happened here. So this is giving me the authoritative name server for ccsf.edu from the top level domain, and there it is. That data was stored at the top level domain, city colleges, and therefore every other edu is up there too. So that's how you see the glue record directly. All right. There's something crazy called a bind version query that only affected bind, and I think it's all turned off now. It was sort of a joke included in the early version of bind where you could see what version of bind was running, but that's not a good thing to advertise anyway. That just helps people hack you. So that's turned off, I think, now. All right. And all right. If you go to ISC squared, they actually had honored it a few years ago, but it doesn't matter. It's just a curiosity. It's not important. So let's talk about server architectures. For a small company, you just outsource DNS. You use something like OpenDNS or another service. So you have your own servers, and you have an internet company, and they provide DNS servers for you with your hosting plan. This is what you do if you use GoDaddy or something. A medium company, you'd have internal and external DNS servers. You'd have some servers here to be DNS servers over your network so external people can find your machines, and that's all you'd put on the external facing DNS servers. And you would have internal servers that are used for your internal company people to find resources that are not public. So you should have the two separated. Now, Microsoft used to make a product called Small Business Server, which was one box that was many things: email, web server, and domain name server, and DNS server. And that led to a lot of people mixing their public and non-public stuff all in the same server, which is a security problem. You really should have two separate servers, one for the public stuff and one for the private stuff that only your internal employees can reach. And a large company will have servers all over the place, and they're supposed to be able to take over for each other if one becomes unavailable, and you typically do that with Anycast, as I mentioned before. So you're going to have a hierarchical caching architecture. Your end users go to caching DNS servers like the router, and that caches data, but then they go to another layer and another layer of caching servers and send recursive queries up here. This will be your local router. This would be like your Comcast server, and that'll be other servers above it. There's typically many layers of caching, which is why I say if something near the root was to go down, you wouldn't even notice or care for a long time because the cached data would serve most of the purposes. And here's Anycast, a little more explanation of that. You configure an IP address on a server, and then you put the same IP address on many servers scattered all over the world, and anybody that tries to get to that IP address will automatically be routed to the nearest available server. And if this one goes down, the Border Gateway Protocol will just route their traffic to another one, so nobody can send a denial of service attack to that IP address. If they try to send a flood of packets, it will get dispersed. So unless you have enough packets to bring them all down, it won't go down. And as long as any of them stays up, customers will continue to get service. That's why this is extremely resilient, and that's why the root of DNS has never gone down. This Anycast is so effective, it has stopped all attacks. And the same thing's true of Cloudflare. Cloudflare protects everybody that wants it for free from DDoS attacks with the same system. They have multiple servers all over the place protected by Anycast, and they have enough fast, powerful servers that it's almost impossible for anybody to deliver an attack strong enough to take them all down. I'm using Cloudflare, everybody should. It means that people can get, that's why if you go to my server, if you do dig for name servers at samsclass.info. They are Cloudflare servers. Cloudflare is my DNS provider. I don't have my own DNS server. It goes there, and all requests to my server go to Cloudflare, which fetches it. Nobody connects to my server directly at all. So my server is like weak and primitive and cheap, and it only has IP version 4. But at Cloudflare, I've got everything. I've got HTTPS, which I don't have on my server. I've got IP version 6. If you do AAAA, I got IP version 6 records. Those are Cloudflare records. They can add stuff that you don't have to your server, like HTTPS and IP version 6, and my cheap little server doesn't have to have any of those fancy features. So it's very handy. Of course, if Cloudflare goes down, my site goes down. And that has happened like, twice in the last 10 years, briefly. Nobody's perfect, but it's good enough. And you can't beat the price. All right, so let's try the other Kahoot, which is here, 2B. Oh, before I do that, let me check. I thought I saw some questions in the Twitch earlier. Yeah, the master-slave stuff, yeah. Spam domains do not allow reverse lookup. Well, yes, that's right, because if I hack into a server and use it to send email with a forged from address that's not really the company name, which is what you do, then when they do reverse lookup, they will find that it doesn't really point to that server. All right, and all right, and the rest of that stuff seems not class related, so I'll just go on to the Kahoots, which are here. 2B, there we go. I remember that was all over the place a few years ago. Somebody had this idea that we must be living in a simulated world. It was popular for a while. Could be true, you'd never know, I guess, but unless you find the pixel size or something. I remember when I was a kid, I asked my mom, how do I know there's really a world out there? This could all be a dream. She said, you don't. I said, I was hoping for a better answer than that, but she was an expert in metaphysics. She said, nope, you'll never know. So you make the decision. If that's true, then there's no point living. The other choice is more fun, so you live with that. And I was hoping for a better foundation for my life than that. And she said, yeah, you might hope for that, but you don't get it. This is all you get. All right. So, what DNS record contains an IP version 4 address? The most commonly used one. That's the A record. All right, stands for address, I suppose. All right, what record contains the name of a DNS server? That's NS for name server. All right. All right, what is inaddr.arpa for? Very strange system. There's probably some brilliant reason to do it this way, but it sure looks backwards and screwy these days. That's reverse DNS. All right. All right, when you open kahoot.it, what kind of query did your computer send? A recursive query is what you normally do, which means just find the answer. I don't care how many people you have to ask. People tell me, and this is what they say in the military, the only three answers to a question are yes, sir, no, sir, and I don't know, but I'll find out, sir. And that's what a recursive query. Go find out. All right, where are the glue records? They're in the top-level domain. They're not at the root of DNS. They're at the top-level domain, like .com and .net. All right, and what record is used to stop spam? That's SPF, which I think is Sender Policy Framework. All right, XRs. Again, they'll have to give me a real name if they want their points. Jacob K, that looks like a real name. And Kate Quigley, that looks like a real name. Good. Good. All right. So let me stop this recording.